we've witnessed formication, crackling sound, and force, and now we have to pick one to think about. Well, this being a physics class, it has to be the force. So let's look at how to calculate the force. You do it with Coulomb's law. If I had to give Coulomb's law a definition, I would simply say it's the force between two charges. So let's imagine two charges on an axis, Q1, Q2, and think about the force between them. Now, force, of course, the electric force is a vector. And I know you're excited to think about it as a vector. I know you love vectors. But we're going to start just thinking about its magnitude, just thinking about the quantity of force. So remember, a vector magnitude doesn't tell you about the direction. It doesn't tell you if it's positive or negative. It's just the magnitude. It's just the length of the vector. So we know it's a vector, but for now, let's just think about the magnitude. So this is equal to Ke, where Ke is Coulomb's constant. And it equals 9 times 10 to the 9 Newton meters squared per Coulomb squared. In some books, you might see a 1 over 4 pi epsilon naught here, where epsilon naught is the permittivity of free space. 1 over 4 pi epsilon naught equals Ke. It's just different ways to write the constant. So for Coulomb's law, it's much more convenient just to write Coulomb's constant Ke. It also has an easy to remember value, 9 times 10 to the 9, if you're working in MKS units, which you should. Next, you multiply by the magnitude of each charge. So here if we have charge Q1 and Q2, since we're just doing a magnitude, here you would just put in a magnitude. Meaning, if it's negative, you don't worry about it. You just make it a positive number, whether it's positive or negative, because we're not thinking about the direction. And then in the bottom, we have the separation, which for now we'll just call R. And it goes as 1 over R squared. So that's your formula for the magnitude of the force. You can look at it and you get some intuitive feel for how this force behaves. You can see right away that it depends linear on each charge. Right? So by linear, I just mean that the charge is to the first power. So if you double Q1, you double the force. If you triple Q1, you triple the force. But it kind of is very sensitive to charge because it depends on each one linear. Right? So if you double both charges, times 2 would go up by 4. Right? So it's a linear with charge, but there's two charges in there. It goes as the square, 1 over the square of the separation, which is kind of awkward to say. I once met a physicist, Knight, who would call it 1 upon R squared, which I think is a very classy way to put it. So the force goes as 1 upon R squared, which basically just means if the separation doubles, the force goes down by 4. If the separation triples, the force goes down by 9. So it's very sensitive to charge and to separation. We can also think about the direction. So this magnitude doesn't tell us the direction at all, but if we start to put actual charges in, or the polarity of the charges, plus and minus, then we can start to know which way the force goes. So without vectors, we just have to state it. When the charges are opposite, the force is attractive. So this would give you the magnitude, but you would have to rely on just this knowledge to get the direction. If the charge is the same, a positive charge here and a positive charge here, then the force is repulsive. And again, if it's the same, even if the charges are negative and it's the same, the force is repulsive. It ain't fiction, it's a natural fact. Now, I'm going to show you that this is true. So we're going to go back to our charged rod. So we don't have little spheres of charge, but we have objects that can be charged. So here's one. We know if we rub the rod with the cat fur, it comes out negative. And here I have a support holding a piece of Teflon tape and a piece of glass wool. So if you think back to your triboelectric series, you know that Teflon is way at the bottom. Teflon is always negative. And this is Teflon tape. It should also come out very negative. So I'm going to use the cat fur to charge up the tape, just like I charged up the rod, like that. And what we should see, they're both negative, so it should be repulsive. So we can make sure that we get the right answer, and sure enough, highly repulsive. Oops, sticks to the metal. There it goes. Can't even get them to touch, no matter how hard I try. Repulsive force between the two negative objects. Glass should be positive. I've rubbed it with some polyethylene bags, which left it positive. The rod is negative, so we can see, and sure enough, an attractive force, because that is the case of a positive charge and a negative charge. We can also use this demo to show that charge is conserved. When I rub, I'm actually transferring charge. We're not creating charge, we're transferring charge. So that means the fur should come out positive. Right? If the fur comes out positive, it should attract the tape. So let's check. It's not nearly as strong an effect because the fur doesn't hold the charge well. But there you go. You can clearly see the negative tape is attracted to the positive fur.